at the beginning of a time horizon. But for the end of the planning horizon, we decided to put only a lower bound, not an equality constraint. Make it easier to solve the problem, to have a feasible solution in case of overgeneration in one of the last time steps. As we had to consider huge grids composed by 1,000 nodes and hundreds of storage devices, we made the difficult decision not to include charge and discharge exclusivity constraints. So as of in the present status of the tool, this is one property that must be checked in post-processing phase. It may happen that in some time step a storage device would both consume and inject power. Otherwise, to include this exclusivity constraint would mean add more integer variable to the problem, and it wouldn't be acceptable for a huge grid size. Loads can be standard loads, fixed or flexible. A flexible load model is this one, where absorbed power is a function of a reference power, which is a parameter, and upward and downward demand shifts, voluntary and involuntary reductions. Each of these terms is weighted in the objective function with increasing cost from left to right. Involuntary curtailment has a very high cost and has been included in order to always get a feasible solution for the problem, but it's not an acceptable solution from the operation standpoint of the grid. Constraints here are that the absorbed power must not be negative. There are also some bounds on the maximum allowed values for demand shift and voluntary reductions. And then the last constraint is that the sum of upward and downward demand shift is rebalanced periodically, for instance, every 24 hours or like that.
What is the difference between these two? Sorry, I could like demand shift whereas voluntary reduction.
Sorry, could you repeat?
The difference between these two, like shifting the demand or like reduction voluntary?
Okay, yeah, the only difference is the direction. Upward demand shift means that the load will absorb more than expected, and downward the load will absorb less. You can think about an electric vehicle charging. It can shift its charging from the afternoon to the evening. In that case, there will be a variation with respect to the reference power. And a constraint in this case is that during 24 hours or a longer period.
The part is like we don't know the uncertain change in the demand, whereas this curtailment or reduction part is when we ask like demand response kind of thing.
Sorry, could you repeat or rephrase?
Like this demand shift terms, there are two terms, upward and downward demand shift. So these are for like unpredicted or uncertain change in the demand, whereas the last two terms are for desired change, like demand response kind of things.
Yeah, the overall framework is the one of demand response. In this case, this is a planning problem, not an operation problem. So we consider also the demand shift for 2050, let's say. So it's not realistic to claim that we already know what an AV will do 30 years from now. These are terms that are included in the model in order to evaluate the possible improvements of in the electric grid by considering the flexibility of loads. So that's why it's important to put realistic bounds on the maximum values of these parameters, and these variables, sorry. Yeah, because it's just a way to evaluate a possible improvement, but it depends on the scenario that one considers. In this problem, since it's a unique overall problem, it's not divided in multiple levels, the seizure is omniscient. What is seek is the global optimum. We already know that this is not attainable in a real use case where decisions are taken in different time steps. So that bounds are very important with that respect. Again, with modeling, the package can use other existing power flow models. We'll talk more about the implementation later. I just wanted to put this slide to say that we had to include also an extension of the simplified disk flow model. This model exists since 20, 30 years, so nothing new even in this case. But we needed a model to that would consider both active and reactive power in distribution network, and there's also the square voltage magnitude. This is a very common power flow model in literature. It's derived from a branch flow model. The additions here are that in order to keep the problem linear, we had to linearize the branch on the apparent power bound. So we built and inscribed an octagon inside the circle that say that the square of active and reactive power must be less than a constant. And the other addition was that we decided to include also transformers in the to have better modeling of distribution grids. So in a standard line, the difference between the voltage on the two extreme buses is computed like that. For a transformer, the extension is quite simple because an addition of a parameter. But we can proceed this way only in one situation where the considered transformer is located just is attached to the point of common coupling of the network, because an additional hypothesis of the model is that voltage magnitude at the point of common coupling will always be at 1 per unit. We consider a transmission power flow model where there is where the voltage angle is a variable, but the voltage magnitude is fixed. And on the contrary, in distribution, the voltage magnitude is a variable and the voltage angle is fixed. So this opens the possibility to consider also transformers and on-load tap changers in a linearized way, as shown. I'll move to the implementation. Here, the software stack, I will start from the bottom. Everything is built in Julia language, and the code make heavy use of Jump.jl, which is the mathematical programming library developed in Julia, which serves to model the problem and to pass the model to external solvers. And FlexPlan.jl is built on two existing Julia packages, power models, which deals with AC grids and related components, and also define an overall structure for data. And power models ACTC is an extension that allow considering also DC grid and related components. The tool is currently lacking capability of importing data from different formats, and the MatPower format is the only supported format for the static data. We have added the custom extension in order to consider AC/DC grids and flexible loads. This data can be ingested by a parse file function. Then data is scaled in order, mostly costs are scaled, so that when they will be added up in the objective function, they will produce the intended results. And I will comment later about the add dimension function, but basically as the time series are expressed as in a linear indexing way, we have to deal with multiple dimensions in the problem. So there's the need of a translation layer between linear indexing and multidimensional array form. Power Models package already defines a data structure for static data analysis, single period power flows, for instance. And the FlexPlan package uses the same format, but and also combines, there's a function that combines static data with time series. The resulting dictionary is built in an efficient way where constant data is not replicated in memory. If you're not familiar with the terminology of power models and related packages, single network means a single operating condition of the system, single time step, whereas a multi-network doesn't mean multiple grids are considered, but multiple conditions of the same system are considered. So multiple time steps, multiple scenarios, and so on. We identified a big gap in the implementation because of Power Models and Power Models AC/DC package, because they are capable to deal with static optimization or multiple time step optimization. But when we move to a stochastic approach, we have multiple dimension. In FlexPlan also, we have the year dimension. Planning years are different one from another one. So when building the model for the problem, the model constraints need several functions to retrieve the correct indexes that have 3 dimensions. In this case, our scenario and here. So there's the need of function that retrieve the index of the same period in a different scenario, or maybe for storage constraint, pairs of consecutive periods in the same scenario, or to go to the last period to build a customized version of a constraint, for example, the final energy state of a battery. So we had to develop a translation layer between linear indexing that is provided by Power Models and related packages and what we needed to formulate the model. So these are some functions included, and in order to build this translation, this add dimension function needs to be specified. It can be each dimension. For each dimension, one thing that needs to be specified is its cardinality. For instance, our problem may have 24 hours, or other properties may be associated with each index of the corresponding dimension. For example, different probabilities for scenarios, or otherwise metadata which are differently from properties and metadata describe the dimension as a whole. This is a parameter for the optimization, for example. So just to show you how the model might be built in the form of a tutorial. In the implementation, what it's needed to do is at first to load the FlexPlan packages, then to load import a solver package to actually compute the optimization problem and to declare it. Optimizer attribute with attribute is a function of jump that is re-exported in FlexPlan, so it's not needed to import jump for this specific instruction. Then the data is built as just shown. In order to construct time series that will be used by the make multi-network function, the user still have to provide a function that put everything in place. It's not already automated. And finally, this is the name of the function that actually build the model and solve the problem. This works for a network which may be a transmission network or distribution network. What is left to see now is how they can be combined. We choose this approach where the point of common coupling buses are duplicated in transmission and distribution. Then we add coupling generators. These generators have a symmetric rectangular capability. With that, I mean that they not only can generate power, but they also can absorb power. And then we add the coupling constraints that establish the power balance, active power balance, of course, and reactive power depending on the support for reactive power that is given by the power flow models chosen for transmission and distribution network. In the case only reactive power is only supported by distribution network, a pair of bounds can be set. So this is this allows to choose different power flow models for transmission and distribution. And the advantage of using only standard network components, so the implementation is easy, but voltage variables are not linked in this way. So this is suitable for planning, but not for operation. Using this model makes the network grow huge. So it may lead to computational problems. So we develop an heuristic that decouples the voltage levels of the grid. That is in 3 steps. At first, you compute a surrogate model for distribution networks. Include them in distribution, in transmission. So the transmission network planning can be solved easily. Then after that, the power exchange at point of common coupling is fixed. So we can re-solve the distribution networks with using the original detailed model. I will talk more about how the surrogate model is built. It's built in 3 steps. At first, we evaluate a base case, which is the optimal planning of the distribution network alone. This considers a constant cost for the energy imported by transmission. Then we try to maximize the power in both directions in order to evaluate the flexibility that may be provided by distribution to transmission. This is done by first fixing investment decision, and then by removing intertemporal constraints, for example, the one present in storage devices. So this translates into several single period optimizations, which are linear programming problems, so are quite fast to be solved. And then the surrogate model is built with a simple algebraic calculation of parameters. The goal is to estimate the single period of flexibility of the network.
One question. So what is the difference between upward and downward case?
Okay, the power is maximized in both directions. In upward case, the absorption from transmission to distribution is maximized. In the downward case, the opposite. What is maximized is the power from distribution towards transmission. We wanted to have these two extreme points in order to compute the parameters of the surrogate model, which is composed by one generator, one storage device, and one flexible load. So it's quite simple. And these parameters are computed in a way that feasibility in the surrogate model implies feasibility in the original model. This is to have guarantees that in step 2, when the transmission network is optimized, the solution recovered is feasible. Costs, however, are an approximation of the cost that would be given by the detailed model. What is preserved are cost variations between different set points. Oh, I am really sorry, this slide is not showing as intended. There would have been two colored areas here showing the difference between the detailed model, which is bound by the two solid lines on the top of the bottom. This is maximum absorption by the distribution network, and here the maximum generation. The surrogate model includes some assumption that translate to approximation to some effects. I will share the slides. Sorry for that. There are two assumptions that one is the independence of components. I mean, the generator, storage device, and flexible load that constitutes the surrogate model will be put in the transmission network and will be operated in an independent manner by transmission. So we have to assure that if a transmission system operator decide to use each of them at maximum power, the resulting power will be still feasible. So this turns this as an effect that the maximum allowed power by the surrogate model in some time step is less than the real one. And the other assumption we introduced is that a variation in the power exchanged with the transmission should produce a variation in the same sign in components of distribution. For example, if the imported power from transmission increases, then all the loads in distribution cannot absorb less. This is a modeling assumption and must hold from each of the loads. In real situation, it may happen that in order to solve, for instance, a voltage constraint, a load will be reduced, and this way another load could increase more than the reduction. The surrogate model doesn't consider this situation. Some results. Here is a test we made by taking a 67 basis transmission network and attaching to it a variable amount of distribution networks. Here is the number of distribution networks attached. The the decrease in computation time is huge in some situation and depends on the amount of the distribution network considered. For instance, with a high amount of distribution network, the time decreases from 6,000 seconds to around 60 seconds, so by a factor of 100. But these results are not indicative when a huge transmission network is considered, because in that case, mass time must be spent in just for solving the transmission part of the network. However, the surrogate model is capable of producing accurate results, both in terms of final cost, also in terms of power flow at point of common couplings, which should have been shown here. Sorry for that again. Anyway, we made this calculation in order to evaluate the quality of results. We took every point of common coupling, every primary substation. We normalized the power between -1 and +1, and we compare the power in every time step in every scenarios, calculating the difference between the two situations with and without decoupling. And the results were then, depending on the transmission network considered, but often the difference is way less than 1%. So in the end, this decoupling heuristic is capable of producing near optimal result in less amount of time with respect to the combined model. And solution quality for what it concerns the power flows is also good, but as no voltage information is shared between the two network levels, is suitable only for planning and not for operation purposes. Okay, last topic is about the vendor decomposition implementation, but I start talking about why it is interesting in this kind of planning problems. This is the problem matrix, which has on the variables on the columns and constraints on the rows. Here are represented 3 different investment periods, 3 years, and we have investment variables, whether I decide to build a storage or not, and in which year, and a set of constraints that relates 1 year to another one. If a storage is built in 1 year, the storage will be also present in the following one. Really? And operation variables are related to power, voltage, and operation condition, the grid, and they must be provided for all the stochastic scenarios considered in the model, but those variables are independent one scenario from the other ones. So if we could remove these complicating constraints between integer variables, then the problem would be easily subdivided in different subproblems, one for each year, for instance, but more than that, because scenarios are independent, one from the other ones. And so if we manage to fix investment decision, the problem can be split in another way, in an integer part and a continuous part, where each scenario is independent from the other one. By doing that, we also have a gain in considering problems of different computational complexities, because if investment variables are fixed, these problems are linear, and there are no more integer variables in this problem. So they can be solved in quite a fast way. This is more or less the idea of the Bender's algorithm. That sounds like that when applied to a planning problem. It's an iterative procedure when there is a main problem that includes master problem that includes investment decision. sub-problems that include only operational decisions. And once the investment decisions are fixed, the sub-problem can be optimized and provide further information to the master problem by the addition of cuts that report a lower bound of operation cost into the main problem. So this is an iterative procedure that can be implemented in two ways. The most easy one considers solver as a black box. So we first solve the master problem, then solve sub-problems. We check if optimality is reached. If not, we add a cut to the master problem, and we start again the procedure. In this way, the classical approach, the master problem is solved at each iteration. The other way is more efficient, and since 90s, since when solvers support the addition of callbacks defined by user, there's no longer need to solve the master problem again, but the cuts can be added along the branch and bound procedure of the mixed integer solver. So this kind of implementation is more efficient, and the difference is huge. For instance, we made some tests with about 300-400 binary variables, and only by changing the implementation, the time reduced from more than 5,000 seconds to just 26 seconds. Because as you can see, the majority of time in this case is spent by solving at each iteration the master problem. Implementation included in the package is a variant of the common vendors algorithm, where the subproblem are not dualized, so it's easy to formulate the problem. It's a multi-threaded implementation, and subproblem can be solved in parallel. But it is widely known that this kind of decomposition also suffers from excessive number of iterations to reach convergence. So, well, in general, the implementation also includes some regularization terms as a mean to speed up the convergence by penalizing changes in investment decisions in consecutive iteration. So we developed this implementation in order to, well, along the development of the tool in the FlexPlan project, but my advice is to start using implementation that are better engineered. There are some implementations are included in solvers like Skip and Cplex. So better make use of that. The one implemented are the advantage that can be customized, which is not the same for the one included in commercial solvers. One more thing, the FlexPlan package. Oh, sorry, there is really some troubles with the visualization of the presentation. Anyway, the package includes several auxiliary functions for data reporting, graphs and plots that show summary statistics about the disaggregated costs, investment decisions, power profiles, also a graph of the topology of the networks. These also are functions that were developed for easiness of debugging, and they are not they are included in the package, but not in the main module of Julia model, in order to avoid unwanted dependencies. But they can be used and imported in using this code. I conclude leaving you some references. First of all, the GitHub repository of the tool is all open source code, so feel free to grab it, use in other projects if you find it to be suitable. And if there are any questions, I'm happy to reply. Thanks for the attention. Okay. Thanks.
It's about the objective function. Can we go back to
Yeah. Which one?
the objective function?
Objective function. Before this one.
Yeah,
Okay.
I couldn't understand how did you decouple the investment cost and the operation cost in terms of uncertainty?
Uncertainty is only considered for the operation cost because the underlying idea is that an investment decision should not depend on climate, on weather, because the system must be feasible with every weather condition, every possible realization of a stochastic time series.
So the investment decisions are more like
Are only in this part, or only in these binary variables that multiply a cost for the investment.
so for all scenarios, your investment decisions converge to one configuration. Is that
Yeah.
correct?
And that decision must be feasible, whatever scenario is realized. So what is weighted in the objective function is the expected value of the cost. But the constraint of the model, which I'm not sure here in the objective function, may impose that the decisions must be feasible for every scenario.
And also another question, you said the scenarios, the stress scenarios are independent from each other. Did you mean like, for example, the load and PV generation and wind generation are independent of each other, or did you mean the growth scenarios throughout the years are independent of each other? Which one did you mean?
I think both. In the end, it depends on what the user decide to provide, because the different planning years will be decoupled if we wouldn't for this part. So it's up to what one decide to do.
So we can just assign a growth scenario, just like there's no scenario tree that are connected to each other throughout the years. They're all independent from each other.
Okay, maybe now I understand better the question. Yeah, there are some constraints between consecutive years, but they are only related to investment. So what is intended here is that you have 3 planning years and 30 scenarios, which are 10 for each planning years. Scenario number 1 for first year corresponds on scenario number 11 for the second year, and so on. But there are no constraints that relate different years with respect to operating conditions. For instance, storage final energy level in 1 year is not related to the initial level of the following year. So in the end, scenarios are completely decoupled.
It's the solution and the constraints for the input preparation. So the growth scenarios are also independent from each other, right? In the input,
Yeah.
not in the solution, in the constraints.
Yeah, I think so. But in the FlexPlan project, it is so.
Basically, it's time dependent, right? You are using storage, so you still create one load profile for whole year or something like that, or every time period is also independent.
No, it depends on how the data is passed, and this is really depends on the implementation the user decide to provide. I mean, from a mathematical perspective, both the alternatives are valid. So in the end, it depends on the data that is passed to the model.
You already create the storage profile or charging discharging profile as an input rather than putting control operations for that, right? There is no control in operations.
There is no, sorry?
There is no control in the operations side, right? Or like switching off, switching on, and so on for discharge.
No.
The part of the solution. There is a model for batteries, and that is that the part of the solution, in addition to the investment, is the optimal dispatch to make that investment for the attractive from the planning point.
But that is like an inner problem, and in outer is more cost effective.
Well, in that case, the dispatching is part of the solution, part of the main problem. Since also we are considering the fact that flexibility is an actual competitor, additionally important of lines of an investment that is part of the asset of the grid operator, the dispatch that the storage should have or that flexible load should have is part is decided by the solver. And of course, you can model anything that is fixed, and then in that case, would model it as a fixed dispatch. This just works. The non-flexible load is fixed dispatch, and you provide in time series. And in that case, for each of the timing horizon, the time series of the values, time series, is basically related to what is fixed. The load is the load profile, is a removal generator, is the profile, the production profile.
And it's pre-decided, right?
Yes, it's pre-decided.
And that was my
You
question.
can add uncertainty to that by considering multiple.
Okay, so for each scenario, you put a probability. So you take, let's say, 30 scenario, and you put, say 0.1 for scenario 1, 0.5 for
Yes,
scenario.
the probabilities come from exactly the clustering the size of the iteration, and also provide any single possible solution with same probability of that management.
What is the total number of scenarios?
Well, and no.
What the time is for 10 scenarios for?
While we managed to perform a planning problem with 100 limited variable, like in 1 week, the entire power system of Italy for 1 week. Also,
4 weeks.
4 weeks. I'd say the way we managed for the Italian case was 4 independent things. Even probably your experience is more valuable. You use the 4 weeks.
So it means we have like 4 scenarios for each season, and the first process data after applying the heuristic method, the clustering method. But you can add as many scenarios if you want. We also did like you use these scenarios before for representative weights for 2 variants, methodological variants, and we actually have a lot of methodological variants in our data. I don't know. From 1982, I think, until 2000. Okay, so you can use that and we probably for each scenario and as many scenarios.
The only limitation and you also
Yeah, in the context of FlexPlan project, the networks we have used are composed by several thousands of bases, maybe 6,000-7,000, so are huge networks, I would say. And with that respect, the problem in adding more scenarios is the amount of data and the amount of memory needed for the computation, because each additional scenario adds a non-negligible amount of data.
I remember it was around 30,000 constraints.
No, way more, hundreds, thousands, 700,000, 800,000.
For every scenario that you add, it's a proportion.
Yes, also the limit we reached in the FlexPlan project about the number of candidates was due to that fact. But if you use smaller networks, also number of investment candidates can be much higher than 100 we are considering.
Is there an exact relation between for a scenario for a time slot in year 1 and year 3? Or they are also independent for the same time slot?
I guess what you mean is like what each stage is stochastic problem, right? Scenario trace rule, but we optimize it for each year. So 2030 we optimize, we have some build candidates and then use that for 2040. So there's no corrective or actions or recourse for the next 90 years.
Yeah, what have been done in the FlexPlan project in the end was to temporarily avoid these constraints and solve 1 year separately from the other ones. So in the end, they were decoupled. The tool is capable of considering also these kind of constraints, but they involve only investment decisions, not operation variables.
So what are these complicating constraints that relax?
So
can you zoom into it, like what these complicating constraints are?
okay, these are just constraints that say that if you build a line in 1 year, that line will also be present in the following year, and that's it. It's replicated by every kind of investment.
But I think that is the big assumption, to not assume that the line will be available the next year.
And so far you solve them separately, no problem, because you solve year 1 for, then year 2 you prepare the data in order to add the data that has been upset previously.
Okay,
So if you couple all of the
make
scenarios,
it not a variable in the second year.
yes, if you solve them separately, so you can manually add this or programmatically. But if you solve all the years simultaneously in the same problem, this is something that we attempt to we want to know, which is the of investments in year 1, also in year 2, and year 3. So in order to make it's probably the storage will be good for the first 10 years, but not good at all for the second and the third one. Probably the line should be preferred, even if the storage for the first year only can be profitable. So this is what we try to do at the beginning. But then we realize that we still have the computational capability to that in the time horizon of the problem. So we split the 3 years in 3. So we didn't deal with these complicated constraints, but the model, as is written in FlexPlan.jl, consider this possibility should be related.
So when you are maximizing your objective function, you are normalizing the cost with respect to the per year cost. Okay.
So there is the discount factor that's considered the part that you should need to consider, which is the cost of the line that you construct in year 1 and how it is weighted for the lifetime of the expected lifetime of the design. So this is 50 years, you consider only the first decade, say for storage.
So if I assume correctly, before you solve this optimization problem, you have scenario generation there, which generates all the scenarios and the weights. And then you select all the candidates and the list of candidates that, okay, I will build a line here, put a storage here, and based on that, you calculate the capex and opex, and that's why you have a single stage optimization problem. So in the set of Y that you have, so you might be getting a bunch of infeasible problems, right? Like suppose building this line does not solve all the problems. So you get infeasibility or
Well, most of the elements have relaxed constraints with consider local payment. And so there is pretty much all the variables, all the variables can be, the solver is able to find a solution which is absolutely feasible, even if not realistic at the end. That's with some problem that were related to 50% of the load that is could pay. Okay, the solver provide a solution, but of course we cannot control that. The only element that is not relaxed or only partially relaxed is the storage. There is the possibility of considering, for instance, for idle pump storage, the possibility of considering inflows from external rivers, and that variable is not relaxed. So in case there is too much water coming from the river, that's idle pump storage. In that case, the problem with regards to, for instance, there is the relaxation of the thought that the storage can absorb and inject energy. It should be double checked.
so at the end you post-process your outcome based on whether there was curtailment or not no curtailment, and then you assess which of these feasible solution makes more sense.
Yeah, and this is also a way to assess different investment decisions, because as every scenario is weighted in the objective function, you may have a particular investment decision that makes as a result that in a scenario half of the load is curtailed, but in that case the cost of the associated to that scenario will be very high, and that will discourage the optimizer from choosing that particular decision.
The selection of the cost of the FlexPlan.jl operator was to select the cost in order to make sure that the investments at the end would avoid infeasibility, because there might be some situation in which infeasibility is seen as an penalization of that particular situation, but the investment would be more expensive than, let's say, than not allowing that load payment. So when we presented the result to the Italians, say that this is not acceptable results, to explain that it was just a proof of concept of what we are expecting for Italy. And so, for instance, load curtailment is something that is considered not acceptable at all. So probably we consider 5,000 euros per megawatt-hour. It can be some situation in which the line would cost more than even 2 hours per year for a network.
But you can, I think you can add like curtailment cost to your objective function to penalize severely that, okay,
yes,
in the solution which is
we can play with the cost in order to make sure that is, I believe, this is the only problem is that when you play a lot of, you have a lot of first cost, also the solution time, we have some problems at the beginning of the project, which just putting some, modifying some percentage in the cost of the simulation increased significantly the operation cost. We didn't manage to understand why this was happening. Probably some problem related to the activity. We have many generators with the same cost and not losses in the system. Probably this problem we have some finding which is the best solution since the result left with
Another question.
Yes.
Consider the spatial distribution of the assets in the grid.
Yeah, this is another problem. So this a grid and topology of the grid is considered.
So the part of the result would be with the assets there at that point.
yes.
At the asset part. And for this, do you consider the equity power flow but also some dynamical constraints. It says that
No, it is a quasi-static simulation. It said probably, I don't remember if the RAM constraints or the storage state, so the start RAM constraints probably are, with some dynamic time rating or something. Or the fact that you can have some peaks in the power.
with the concerning for the inertia and the grid, that its spatial distribution is more important than its diagonal amount. So that would possibly mean that in order for the grid to be stable, you would possibly need to add the StatCom at that point. That would change the cost.
Yes, I think
No, the optimal location of investments is not considered.
I'm thinking about inertia, so the fact that some devices can provide additional services in addition to, let's say, congestion management. So we usually just congestion management. Security constraints is the reliability analysis is included in.
No, but contingency states can be included anyway as scenarios. Instead of passing a different set of operating conditions for renewables and demand, you can also pass a different grid topology for that scenario.
This is meant for long-term planning, so we just amount of constraints that make the problem feasible, let's say, in addition to you agree that the fact that, for instance, investing in storage with respect to a new line be more beneficial for what concern additional services that can be response to some the CEO providing support to synthetic inertia or services such as primary and secondary applications such as and I know the acronyms, but however, previous restoration of the server,
You would have that also with adding the line because it changes in connectivity. So it also changes.
Yes, absolutely. And this is something that is not included, but can be necessary. Also, we have some with that we needed to limit the amount of constraints, even the load model, load flexibility model is being relaxed to 6. Since for the shift, we consider a model that is very similar to the one of storage. But at the end of the day, the energy balance will be compared with the baseline comparison. But there are other constraints such as the grace period or the fact that you cannot ask to any time of the day that specific possibility. But the time shifting is actually moving atomic load, so something that cannot be changed in our profile. That's after the spin relaxed, since say the planning tool is just a tool that provides signals on where the flexibility would be profitable for the system, but then which kind of specific flexibility, such as is a voluntary load reduction or tenancy done in this particular way, something that is done with possible. So what's that can say, okay, this the line is definitely the best investment we can get, or in this point of the network, storage might make it price. But then how the storage is operated, or which services should be provided by the storage, something that is decided much closer to the time horizon of the system.
I see a lot of similarities with another GDAP package being Spine. You've ever heard of?
I've heard about it a couple of years ago, maybe, but never investigated in detail.
They also use vendors decomposition. As this, so in your RSE creation. But it might be interesting to just have to look again assessment as it falls. Since a couple of years ago.
Yeah, sure. And do you know whether it's based also on power models and related packages? Or
I think it uses the original formulations,
okay.
but it might use
Hmm.
I'm still learning it.
Okay, thanks for attending. And